we're gonna do this first part together. And then I'm gonna have you get your lab set up. I'll walk you through what you're collecting, how to find it, and then we'll take our quiz for the last 20 minutes. First thing I want you to do, we're gonna start with the background. You're going to draw a picture of a low-pitched sound. In fact, just ignore the low-pitched part of it. Draw a picture of a sound wave. You're going to use dots to represent the particles in the air. And I want you to draw and label where the compressions are, where the rarefactions are, and where the high and low pressure points would be. And we did this in the last quiz. What would a wave length look like? So go ahead and draw your first low-pitched wave. Draw your wave part of your air particles with a sound wave traveling through it. We'll call this, Marina, turn around please. We're going to call this our low-pitched wave. Pitch is related to a specific variable in our wave speed equation. Can anyone tell me what it is? Vincent. Frequency. So if this is the frequency for my low-pitched wave, I need a higher frequency. So for my high-pitched wave, however you drew yours, I want to make sure that you show you've got more rarefactions. You're going to have some spread out portions right here. Maybe I'll remove a few of these dots. And then they're more frequent. They're going to happen more often. So here's another compression, a rarefaction, another compression. But I want to see that there are more of them closer together, which shows more frequency. Okay, so that's going to be your high-pitched wave. Now, when you're looking at these, it's pretty obvious. We already know that we've got our compression and our rarefaction. So where do you think I would have my high pressure and my low pressure points? Where would those variables or values be in this Avery?
I think high pressure would be where compression goes.
Exactly. So high pressure in the compression and low pressure in the refraction. Pretty obvious, right? And then the wavelength, I expect you guys to know that it's from the beginning of a compression to the beginning of the next compression, or beginning of a rarefaction to the beginning of the next rarefaction, or from middle to middle. Any questions on the diagram? Our lab is this. This is what you're going to sketch once you get into your groups. What you're going to do is you're going to take either a frequency generator. I have these apps. It's under Firefox, and it'll create a tone. Like when you're tuning an instrument, for those of you who play music, you have a tone generator, and you want to make sure that the tone of your instrument matches the tone of the generator. So it's going to create just a constant kind of beeping sound or a constant tone. I used to use, before we had apps, tuning forks. So I provided both because I feel like students have more fun playing around with tuning forks. The problem is I don't want you banging these tuning forks against the table. I tell my students to hit it against the sole of their shoe because it needs to be hit by a rubber mallet, which your shoe is rubber. It'll create a tone just like your tone generator, and you want the tone to create a frequency into your tube because at a very specific length, your tube is going to give you resonance. So what does resonance sound like? It's going to be a position at a very specific length where your tube starts to give you a high intensity of sound. So it's going to get louder at that very specific point. So we did a lab on harmonics, and we tested out different types of harmonics. We had a situation where we had two closed ends, like a guitar string. We had a situation where we had one open end and two open ends. So in this scenario, where I'm creating a sound wave through this tube, would it be considered a two fixed end, one open end, or two open end harmonic? What type of scenario would this be? Karis? One open end. Because if you notice, I have water here, and the water creates a closed end in your tube, and then as the wave travels through, it's going to come out the open end. This is what the wave looks like. Node to antinode. How much of a wave is this? Is it half? Anya? It's a quarter. So this is where we go back to standing waves. A standing wave, if you go from a node to a node, one loop makes one half of a wave. So half of a loop makes a quarter of a wave. Now, when you are doing this, I'm just going to draw on top of, this is my beaker, this is my water, this is my tube. And remember, the tube will only resonate if it has a specific wavelength. So once it resonates, you're going to get your first harmonic. You might get your third harmonic, you might get your fifth harmonic, but what we're looking for is just the first harmonic, which is 1/4 of a wave. So this is answering, how many open ends does this have? 1. Based on what you learned in standing wave simulation, you're going to draw this here when you create your lab setup, but you're going to draw what your standing wave looks like for the first harmonic, where the nodes and antinodes are in this scenario, and then you are going to tell me in the question, part 6, what fraction of a wave does this give you? So that's going to be 1/4. Okay, so we basically completed this whole first page together, and then you're going to do your sketch once you get into your group. Question?
How do we know that it's 1/4 of the wave, and why is it there at the top?
So it could actually be, you could have a third harmonic. So I'll show you a scenario where we have maybe the tube come up higher. So this third harmonic would look like this. It'll create one wave and then an antidote. And this could be the most common source of error that we get in this lab, because this is first harmonic and this is third harmonic. And you're going to hear both if you lift your tube up high enough. So the trick to doing this is understanding our inverse concept, because you should be seeing a pattern. If you start out with a low frequency, I want you to start out with maybe 250 hertz and then work your way up. If you start out with a low frequency, what should your wavelength be based on our proportion? It should be higher. Low frequency is a high wavelength. And so if you start with a low frequency and work your way up, you should see the wavelength getting smaller and smaller and smaller and smaller. If you notice that your wavelength jumps up to a really high value, you probably found the third harmonic, and you need to go lower to find your first harmonic. Does that make sense? How do you find the harmonics is the hard part. The reason why is because we're going to have each different group creating a different tone and trying to listen, so it's going to be a little bit hard. you want to have your ear pretty close to the tube. And when you create your frequency, if you're using the iPad, you want to turn it up to its highest volume. And the sound comes out the bottom. So you want to hold the sound to the top of the tube. And then as you lift the tube, that sound is going to find a position where it actually increases in volume. It increases in intensity. Now, there's going to be a lot of room for error because as you listen for that position, you're going to have, your partner with a ruler trying to measure it. You're going to have to try to hold it as still as possible. You're going to have to ignore all the other sounds in the classroom to see if you can find that high intensity sound. But the best thing you can do, I highly encourage you to do, is to make sure that when you are trying to find the wavelength, that it fits the pattern of your frequency getting higher and your wavelength getting lower. Okay? So, what I want to demonstrate is what this frequency sounds like. Let me see if I can find a good tuning fork first. It's easier to hear at high frequency, so see if you can hear it. Even from there, you might be able to hear it. Do you hear where it kind of increases in sound? You can't hear it. So, there is a position where if you listen closely, and especially if you're close to it, you can hear a intensity and volume. So you're going to stop at that position because if you go any higher or any lower than that, it's going to diminish in sound. It's going to be hard, I'm going to tell you, with all the different groups doing this at the same time. So if you can find a way to spread yourselves out and isolate and also have one person kind of having their ear pretty close, you can use these iPads, which might be easier because you can start at a low frequency and work your way up. But working with the tuning forks is a lot more fun. I want you to use a different frequency each time. So in your chart here, you're going to use different frequencies. You're going to find the period. How do you find the period of a frequency? 1 over your frequency equals your period. You're going to find the length of your tube. So this length is from the water to the top of your tube. But that's only a quarter of a wave. So in the next column, how are you going to find the wavelength? Multiply by 4. Okay? Your goal is to collect this data today. We're going to do the rest of the analysis next class, but I want to make sure that you get 6 different frequencies and calculate 6 different distances so that at least by next class we can analyze and do our graphing and all of that stuff. But I don't have this material next class. I have to pass it down to Ms. McGarry and Ms. Lee, so make sure that you are productive today. Any questions? Okay.